All right, thanks. So this is actually the concept of the method. You know, intuitively think about the surface of the Earth and torus or things like that. They gave example, like for example, 2-hour robots. It could have been a patch, a square, but if one of the two joints, for example, have a complete rotation, the segment becomes a circle. So you could have a cylinder. If the other one also total rotation, you get a torus. Remember, this is what I indicated last time. All right, then the important thing is that now we can connect, if this is smooth, every point of the manifold at the tangent space, then it means you have, if you have a trajectory at a certain point in time, if the trajectory, a curve in differential geometry is just to parameterize elements on an interval, which is a part of real numbers. Could be time, could be something else, it doesn't matter. And then each point you can define a tangent space. In that tangent space, then you have the velocities of that curve at that point as something, is an object which belongs to the tangent space. This is the extrinsic representation of tangent spaces. Frederick gave an intrinsic representation, but it's not one I will use. But of course, the intrinsic is much more powerful, but this gives a more intuitive idea of what is going on. And then here, this we have a tangent space. So we have a tangent space, which is a vector space. So with vector velocity can sum, you can multiply by constants, so it's a vector space. And you know, for all the linear algebra stuff we did, that if there is a vector space, there is a dual of the vector space. And the dual of the vector space are basically the space of all linear operator on velocities, which for physical reasons, in fluid mechanics, would be, for example, the space of forces, but also the momentum would belong to that space, because of Newton's equation. There are objects that intrinsically belong to these tangent spaces and are objects that belong to the dual. Okay, and it's very important to make a distinction. Okay, so the example here, if you have a velocity and dots which is attached at M, so vector is really attached in a nonlinear setting, it's important to say where the vector is attached. Okay, this is a notation, this is called a tangent bundle. This is a tangent space in M, which of course, and the tangent bundle is the union of all the tangent spaces at all points. And then you have the dual space, the standard notation would be using of linear algebra. And then the cool thing is that if they are in the same point, then you can pair these two guys, and then you can talk about power in this case. Okay, so you have a real intrinsic invariant real scalar number. Now, and then we go to a concept which will in robotics will be used all the time about a nonlinear map. So if you have now two manifolds, and you have a map between two manifolds, and this map is smooth. Why can you talk about smoothen? Well, you can't talk about smoothen because if you have then a map here, a chart, and here a chart, and then you can express the Rn, the relation between Rn's, and everything is diffeomorphic, then if that map is smooth, it means that you call that this map, you call it smooth. So it's basically, it's always smooth if all the maps of the chart are smooth, the map between the charts are smooth, roughly speaking, okay? You can precisely define that, I will not do that. The important thing is, this is, for example, kinematics in robotics. So this would be a configuration space, and the 2-hour robot could be a torus, this thing, and this one could be, the end effector points, where the end effector is. And this would be what is called the direct kinematics in robotics. What is important is the fact that once you have a nonlinear map like this, you can consider a curve on the left side and a curve on the right side. In the case of robotics, you will have, for example, the joint, a curve in the joint space, and you have a curve in the workspace. Okay, and then if you are in a certain configuration, then you have a certain position of your. So if I'm in a certain configuration of my body, then I could say, well, for that configuration, I have that point in the workspace. And the cool thing is that now, around those 2 points, you can look at all possible velocities. If you would be there and you move in certain direction here, what would be the direction move here? Okay, so you can actually consider the tangent space there and the tangent space on the other side. Okay, and then you can define a map, because then the differential of this, okay, which is what you have learned as an analytical Jacobian. Okay, if you have the map that maps velocities here to velocities here is called in differential geometry is called the push forward. And it's a map that goes, you see, from the tangent bundle there to the tangent bundle there, such that if you're in Q and the corresponding is X, okay, this is related to that point, then a velocity is mapped to the corresponding velocity on the other side. That is Jacobian robotics that is used all the time. The analytical Jacobian, not the geometrical Jacobian. I will come to that later. And then they are joined, when we did linear algebra, we said if you have two vector spaces, which are these two vector spaces in this point, Q and X, if there is a map, there is always a map in the opposite direction of the dual spaces. Okay? So if you have the velocity maps like this, then you have a map of the force in the opposite direction. And in fact, if you remember, it's actually even the same thing. It's not, as a map is a different map. But tensorially speaking, if I write like this, okay, I can contract the I index, if you remember this discussion, and I have something like that, okay? But I also could contract with the same map this index, and let's call it force bar, okay, I, you see? So the same object, I can use the same object as contracting one index is a map on the velocity in one direction, and the same object is a map of the force in the opposite direction. It's really the same thing. It's not, as a map is a different map, but it's the same nature, it's the same thing. And this is something which is, pretty deep if you think about it. So you can never see a map, a differential map separated by its dual. It's the same thing. And that's what all is going to be embodied in the modeling we'll start today. Okay? That, when there's a map between velocity, there is also a map between forces. You should not even separate it. It's the same thing. And if you take them all together, modeling becomes very, very powerful. And this is called the pullback. Okay, the pullback map, you see the back in the opposite direction, is from n to n in the tangent space, and the pullback is from n dual to m dual. Okay, that is the transpose Jacobian in robotics. You would have a map of the velocity like this, and the transpose Jacobian that I told you. Remember in linear algebra, if you have a matrix that represents a linear map, the transpose is in the basis that you have chosen is the representation of their joint map, which maps the dual vectors in the opposite direction. Okay, and that's a cool back. So this is the important relation between linear algebra and differential geometry that connects all the stuff we've learned in linear algebra that we spent a number of lectures on to differential geometry. And this will be the chord in which everything pops out, basically. Okay. Well, the example of manifolds I gave it again, so I will skip that. All right, now here we go. Now we have enough background to start talking about core-based physical modeling. And just as a note, when I came to the Netherlands in '92, some of you were not born, okay? And I was coming here, and because my now wife and girlfriend was Dutch, and I needed just to have a project to come here. So, and then there was this guy, Peter Bretel, was a colleague of ours, who had a project called Olmeco, and he was using this stuff called bone graphs. And so I was offered to have jobs. I needed to learn this stuff. So I looked into it and really didn't get the point. Find another way to do things, but and I really didn't get the point. And then after I started working with this, at a certain point, I said, "What the fuck? This is really, sorry the word, this is really deep." And I've been working since '92 until now on the same stuff, basically. Okay, so this is really something which, once you get the power of this, and Frederick Schuller, that some of you know, when we saw that, and because it actually came to Twente thanks to that, because we met once at Kukai, it was at Erlangen to the time, and he was like, this is amazing. This is a way to look at physics, which I've never seen before. And he's a theoretical physicist, okay? So that's what I will try to convey in this message. And I will start to build first the bone graph language, but it's just a language. The concept is deeper than the language itself, okay? And I will try to give you the language at the same time the concept, okay? So then and please stop me, because I would like to convey this, the groundbreaking way of thinking about this. One thing that you have learned is this duality, right? That's why I spend so much time in linear algebra. You have to understand that if you have tensors that have this duality, you have vectors and you have covectors. and they are not the same spaces, but they are very much related, because once you have a velocity, you have something which is. Duality, I think, is the most important concept in all of physics. Okay, so what is physical modeling? Okay, physical modeling is to distill the answer of physical system, okay, and describe it with tools and which are useful for what you want to describe. If we go to the Enlightenments and to go to Descartes, one of the, the one that basically gave us the relation between geometry and algebra, by putting axes. The Cartesian axes come from Descartes, okay. One of his major contribution to philosophy was the way of reasons, treatment on reason. And was saying, if we want to understand things, we need to dissect them back and back and back and back, and then find the decomposition until the essence of every single thing. And then once we understood this, we can then recompose it. Only in that way we can perceive complexity. Okay, so it's very important, the structure of decomposing. And Descartes says, "Cogito ergo sum," so I think then I exist, because you got to the essence of one of these things. Okay, and that's what we'll try to do. And board-based modeling will try to do it in a way which will decompose a physical system, will tear it out to understand the essence of the various parts composing it. Okay. And the important things, of course, about physics. That's why it's physical model. Okay. And the word physics is fundamental, because what is the in classical physics, the glue of nature? Energy. Okay. Energy is the glue of nature because it's the preservation, it's the embodiment of the preservation of physical laws in all domains. Doesn't matter if you do electrical, magnetic, mechanics, fluids, it doesn't matter. Energy is the glue, okay? So you want to be able to keep that as a guiding line in what you do. And that's not what block diagrams do. Block diagrams are just a nice way to draw equations. Okay? That's the core message. And my conjecture is that any physical system with lump or distributed parameters can be modeled by the composite diaports. And if you do it in the way that preserve the structure, you see things and you are able to do things that are absolutely novel in the way to think about how to model physics. Even robotics itself, which is a reasonably simple physical domain, if you think about, finite dimensional, suppose it's finite dimensional. They are, and now I'm writing actually a paper on that, even the fact that you have a robot that can interact with the world. How do you describe interaction with the world? It's not that you apply a force, like force control does. Okay, it's the impedance. Is how you want to describe the real interaction with the world, and that's something that people have not done. Don't usually do in robotics. Okay, and I prove a number of theorem and other things I'm actually writing down, which is a conjecture I had, which I now prove on that is really you cannot do otherwise. Basically, so it's really decomposing system and making open. It's about open modeling. If you model something and let you have the model like that, done. But if you want to do open modeling, you want to model a subsystem in such a way that that model that you make makes sense, even if you then will use it with other things. It has boards which are open, and then it doesn't matter what you attach to it, it still makes sense by itself. That's open modeling. So let's take an example. Okay, let's take a voltage divider. If you get this voltage divider, typical example, you have an infinite impedance, and then you write a transfer function between voltage input and voltage out. Okay, and then you say, okay, well, that's the map between the voltage in and the voltage out. Now, is this true? Okay, and some of you may think it is, but it's definitely not. Okay, because what it was the case is previously is that the hypothesis is that you have the transfer function. Another hypothesis is that load, which is reported there, that load, okay, is infinite impedance. But if you now put a second voltage divider, that's not the case. Okay, so that's not anymore the case. So this is absolutely not true. It's wrong. And the reason is much deeper than this example. Anytime you want to interpret physical system, you always have a bidirectional relation. Action, reaction, third law of Newton. Okay, doesn't matter if you do electromechanical system mechanics, fluid dynamics. Whenever you do something on a system, the other system does something on yourself. There is always a bidirectional way. And I'll show you later when I introduce a number of things that it cannot be otherwise, because otherwise you would get absurdities in your modeling. Okay? So the point is that with physical systems, signal modeling is, well, I say I want to be politically over, is never, okay, suitable. Actually, if you want to do proper physical modeling, which is open, is never suitable. Physical energy, as I say, governs the dynamics, okay, and you always have a bidirectional, nonlinear, whatever effect. And to model and control real open systems like robots, signal modeling is really not what you should do. Block diagram is not really the solution. Block just gives a causality relation in evolution of computations. Physics is not computation. Physics is not computation. Okay. So this is, for example, I was at ICRA last week, and there was this talking, for those of you who were there, and there was this statement of Wolfgang Bugart, who basically said, you know, learning can do everything. Forget it, you know, learning cannot do everything. And he said, because this is the computer science way of thinking, that if you have enough computation, if you're fast enough, then you can repeat things. It's not the way physics works. You know, we know that sampling and you know, Shannon, for example, if you look at you know, there is a limit if you want to interact with physics about the bandwidth that you have if you have a certain finite sampling. Okay. So robotics is the interconnection of multi-domain parts, and therefore we need something more, something else. So now we will go. I think some of you may have seen this slide because I've used it a couple of times. But this is, I think, I tried to put in these slides the core of what we're trying to do. So if we have a physical system, suppose this physical system is this blob, this blue blob, which is on the slide, and then we axiomatically start from the point that, you know, physical laws are important because they are preserved. They are the guide and the model of all the things. Okay, and what do you say? Yes, and energy therefore is something you want to preserve. So now, if you want to do a conceptual decomposition of your system, okay, you want to basically say, okay, this I want to decompose it. It's like, for example, an harmonic oscillator. An harmonic oscillator, and you want to say, okay, why does that behave like this? What are the things that actually make this harmonic, you know, what I measure, what I see? And then, of course, we are as engineers, you know that if you have, for example, a mechanical harmonic oscillator, which you have the mass and the spring, you conceptually tear out the mass and the spring. Okay, and then you say, okay, the mass has a certain physical laws that I know, spring has a certain physical law that knows, and in harmonic oscillator, totally energy is conserved, but we know that the energy goes from right to left and left to right. That's the conceptual understanding of what an oscillation is, right? But we want to lift this idea. So we want to, the general system, want to tear it out. Another question is, how can you do this in a way that, what is the structure that I need to describe this interconnection in the most general case? That this would work with anything. It would work with PDEs, that would work with mechanics, electrical field, electromagnetism, anything. Okay? What is the most general structure? Okay, that's the question. And what we want is that this structure should be such that it's able to preserve this energy. So in the sense that if you have a total energy, then you know that once you decompose, you can associate an energy to this part and an energy to this part. Okay, because this block is the abstraction of that part of the physical system. You want to associate an energy, and if you want to do this, you want that the sum of these two guys will be the previous one, because you know your decomposition is conceptual. It's not that you change the system. You want to model it, you conceptually decompose it, right? So if that's the case, you want basically power, you know, power transfer. So you want something that has this decomposition. If the energy goes down here, goes up there, the energy goes up there. That's, you know, the minimum you want. And I didn't tell you whether this is a mass spring system, whatever. This should always be the case, because if that's not the case, it means the energy goes somewhere else, and that's inconsistent because I want the energies preserved. Okay. Good. Now, what we also know is that, as I said, and I will show you it again and again, these things are, you know, these two systems will affect each other. Okay, these will affect each other. So the system part one, okay, will affect part two, and part two will affect part one. So I don't know what these E and F are, but there will be objects which I will try to find out, such that they describe the effect that part one has on part two. And F, I just call it the thing. I don't know what mathematical structure, we'll come to that in a moment, or whatever, will be something that will affect the opposite direction. Okay, so, and I could have written the opposite, doesn't matter, you know. And there will be function of time. Why? Because time is the evolution parameters that we want to describe about dynamics. Okay, in classical physics, relativistic physics, I mean, in classical physics, non-relativistic, time has a special nature. In relativity, in general relativity, you have another parameter that you can use. It's an evolution parameters. And then you can see how, on the basis of that parameter, time changes and configuration changes, for example. Okay? And then there is something which is called the Hamiltonian constraint, which is using the general relativity to make this clear. So in general relativity, time is just another variable as configuration. But in this case, time is a special parameter. Yes?
Maybe a very stupid question, but why can't you have a arrow pointing both ways? So just
I will give you the reason. It's definitely not a stupid question. And the reasons for that will become clear when I finish introducing this. I will definitely come back to that. But it's a very plausible question because that's how the two possibilities, like this, like that, or like this, right? Mm-hmm. So, and I will show you that intrinsically I give you first the intuitive reason, okay? If that would be the case, it would mean that the system can give both variables would be able to, you will see in a moment, to basically control everything. So it means that you would be able to represent the evolution of something which is independent on this boundary or whatever it's interacting with that, which is conceptually goes against Newton's third law. It's impossible. Okay. So the fact that I say I want to move with a certain speed, but if there is a wall, I can't. The wall will stop me because I interact with the wall. Okay. So there is always it's really the bidirectionality and the fact that it's not like that. You will see has a very, very deep meaning. Okay? And I will come back to that later. Other questions? All right, now here's the core. Now, what is the nature of E and F? Now, mathematics, okay, is the biggest creation of human mind, as I said, and gives you the model. What is the structure? What is the minimum structure you need in order to describe this concept that you want to describe? Okay. That is the question. And what we need, we said, okay, what are the two things? We know that, and I'll come back to that, this bidirectionality. That's one thing. And the second thing is this thing of power preservation. These are the only two things which really we want to represent, right? So, and the power is function of t. So I want something that relates these two variables somehow to the power at that instant of time, to the transfer of power at the instant of time. Now, if I say I have two objects, okay, which without any other structure, I want that these two objects somehow, if I combine in a certain way, it gives me a real number, power, which represents the transfer. What can these two objects be? Cool. Okay, so, and we'll see that all the other things will come handy. But you see that the answer is it's very simple. The mathematical structure, the minimum mathematical structure that you need in order to talk about this, and you see, I want bidirectionality and the fact that combining these two variables that describes how these things relate. I describe the power. We have learned in linear algebra that is actually the fact that if you have this element belonging to a vector space and the other element belonging to the dual to the vector space, you know that there is a natural way in which these two objects can be paired, and the real number that comes out could represent in your modeling the power transfer. Okay? This is the core of all port-based modeling. Okay? And the cool thing is that, this is very, very general. This vector space could be a real number. This vector space could be a Lie algebra. This vector space could be form. This vector space could tensor value form. And with these things, It's always the same thing. You have duality properly defined, and it will be the way to decompose anything in classical physics. It is mind-blowing that this works, and during the 4 weeks, we've been able to show that this is indeed the case. That was an hypothesis, but it's indeed the case. You can couple then nonlinear elasticity to fluid dynamics and this goes further also in the relativistic sense, but it's something we still have to write down. So very simply, if you're in electrical circuits, the vector space would be a real number, like current and voltages. Okay. If you go to multibody dynamics, you will see that precisely the vector space will be SE3, which is a bit more than a vector space, and you'll see why that structure is needed in multibody dynamics. SE3 is a vector space in linear algebra. What is a linear algebra? Is nothing else than a vector space plus an extra structure, which will be fundamental, as you will see, because of symmetries and stuff. But if you want to go to strain, it turns out that also for infinite-dimensional systems, like elastic deformations and fluids and whatever, you have still a field, and then you have a field which you represent with a certain object, and you can define a dual field. And if you have that field and the dual field, you can combine this field and the dual field, and will be a new object which you can integrate. And that integral will give you the power flux as a power density. It's just magical. It always works. It always works. Okay? And I will give you an insight on infinite-dimensional system after we did the old stuff on multibody dynamics. Okay? This is the core. Is this clear? Please.
What's not clear to me is why it should be why they should be linear objects. So F and E, I should be able to combine them somehow and get a real number. And if you tell me that they're linear objects, then I accept that, of course, they should be dual vectors. But
you will see the moment, because when we start building this up, you will see that the fact that they are linear spaces is precisely what you need in order to decompose. And that comes from the fact that, for example, what is in the branch of engineering, if you wish, the place where graph theory and decomposition of system has been the most powerful in electrical engineering, right? And you have Kirchhoff's laws, and you have your networks and this kind of thing. Well, it turns out that that's precisely why you need it, because every physical domain is exactly the same. That people in other fields have not recognized it, and you will see that we'll introduce objects which are called junctions in bond graphs, which actually represent Kirchhoff's laws. And then you will see that you will need a vector structure because you want to be able to sum efforts and flows. Because now I decompose only in 2. But sometimes I want to compose in 3, and I want to say how are these 3 elements connected to each other. So it will become all clear. But there is it is a fact that the vector structure and therefore the linearity is actually very fundamental. You will see. Also, you will see because, for example, all the nonlinear stuff, you see that the composition and the way you define the graph is, let's say, the linear thing. And in any physical domain, the nonlinearity appears in the constitutive equations, okay, which appears inside the. We'll see that all, okay. But that is deep because it means that that's why tensor calculus is so important, because tensor calculus, which works as tensor field, it tells you that in each point things are linear, because we know that if we're small, things are linear. So it all comes from that. Okay. Any other questions? So notation-wise, this is what Painter at MIT introduced in bond graphs. He says, you know what? If I then decompose the system, I want to talk about interconnection between these 2 parts, and there are always 2 variables involved. All like this or the opposite direction. I need an object that actually represents these 2 objects at the same time, and he called that a bond. Okay. So this is a power bond, and you recognize it's different than other because it only has half an arrow. It doesn't have a total arrow, so that's the notation that Painter introduced in the 80s, 90s, 80s. And then what you see is, of course, this arrow has a direction. Okay, it's a half arrow, but it has a direction. What does the direction mean? Well, if you know the efforts and the flow, and you take them both, and you pair them, you get a real number. Real number can be positive or negative. If the real number is positive, it means that the power is positive. means that the power goes from here to here. So if it is 3, it means that there are 3 watts, for example, going from here to here. If it is -3, it means that there are 3 watts going from here to here. It's the orientation. And that's the sign gives the orientation. Okay. And then so the power from 1 to 2 is basically this in this context. Okay, you have a certain flow as function of time, certain mass as function of time. You know, by definition, the effort, well, it's called effort. I didn't tell you that the dual vector, the co-vector applied to the vector, okay, is the power. Okay? And this property defines any possible vector space. And you will see why in these 2 questions. Please remind me if I didn't answer before the end of the lecture, because these are very important things. The first one was, why not both in the same? Oh, I can tell you this now. Now, suppose I have enough, because now, if I use this modeling, suppose that part 1 could set the efforts and the flow independently of part B, we would not have an energy crisis, because part A would basically be able to indicate the power independently of what this guy does, because the pairing is power, right? So it's like, you know, suppose that we can, there is a physical object. There's a physical object that can set the efforts and the flow, well, that's the name I give to these things, the vectors and covectors, both by itself, independently of whatever is attached to it. That means that that object could pump power out as much as it wants, or could suck power out as much as it wants, is the only one who decides. Which of course makes no sense. We know that that's not the case in physics, right? So that is the reason. So the fact that it's really bidirectionality, it cannot be otherwise. I didn't say that should be like this or the opposite. But in any case, I can tell you that it's not like this or not like that, for that reason. Because otherwise there would be an entity which could decide the power flow independently to what you are attached to. Impossible. Okay, that doesn't answer your question? Okay, and your question was more related to linearity. I'm coming to that, yeah. Okay, so. All right, now a bit of notation. So this is just notation. So now there is a very difference between causality and the description interconnection. So if you have this object, you see I could have effort out and flow in, or flow out and effort in. Okay, that is a causal thing. Okay, but if I write it like this as a bond, and I do not write anything else, I do not tell you what is what. So it could be that the effort goes in and the flow goes out, or that flow goes out and the effort goes in. So the direction of this bond, it does nothing have to do with this direction of the 2 signals. This is only the power direction. Okay. So are 2 independent things, very important. Okay. So these things, the bond gives you the direction of power, independent of causality. It can be like this, doesn't matter. Okay. But you see that, for example, if this is like this, if I want to invert bond direction, you need to put sign minus, okay, because the power invert direction is changed. Okay. But then, therefore, what you then have, you can have all the different combinations, and the direction of the signals is this bar, which is called the causal stroke. Okay, it's like yet another direction thing that indicates the direction of the E, the effort. Okay. You see, for example, up there, the effort comes out, and therefore I put the stroke in this direction. In this case, the effort goes in, so I put the stroke on this direction. And you see, it's independent of the direction of the bond. There are all the possibilities here. So the bond, you know, can give you the direction of power. So this is what is called an acausal representation. I'm not telling you who's giving the effort or the flow. I'm just telling you what is the positive power. That's it. If I furthermore put a stroke, which can be like this or like this, I tell you also the causality. Physically speaking, causality is actually not needed, because if I shake your hand, and we have 2 hands, we are 2 humans, you give me the force and I give you the velocity, you give me the velocity. You don't know. You know, it's conceptually speaking is not important. Of course, when you do calculation in a computer, it's a causal machine. So you need to do this analysis, which is called causal analysis, because you want that to the description, which is acausal. You want to tell how things are computed, for example. And actually, that thing will give you, and I will not have the time, but I will try to give you an example, is absolutely fundamental to understand the number thing. For engineering, it's mind-blowing what you can do with that. I'll give you an example of two masses in oscillation and frequency of a transmission. And people that don't have a Baumgart's background don't see the power of this stuff. So it's not only powerful from conceptual point of view. For engineering, it's just amazing. Okay? Is this clear? This distinction? So you have two things. You have a direction of the power, positive power, and you have a direction of the causal stroke, which is the direction of the causality of the efforts in the flow. Okay? Yes.
Which side does the causal? So in the top left example,
Yes.
you've got the causal stroke on part Y. Does this mean the effort is going from Y to X?
Yeah, so if you have a segment, which is the line,
Yeah.
You asymmetrically decide where you put the stroke on the one side or the other. If you put it on this side, it means that the effort goes toward that direction,
Towards
toward where the stroke is, the
So-
causal stroke.
So in the top left, the effort is going from X to Y.
Now look,
No.
here. You see, this
Yeah.
is the line. Now forget about the bond.
Yeah.
This is the line.
Yeah.
So here there is another object.
Yes.
Okay? So it means that the effort goes from here to here.
Yes. Okay.
And here it goes from here to here. You see? And this, the bond is like this, like it doesn't matter. So are two independent things.
Yeah.
Okay, so
No,
you can
that's
have,
what I mean. The vertical stroke. is
yes,
when-
and if you
when
put it on the
get
other
to-
side,
Yeah.
it goes like that.
Okay.
Yeah, is that clear? So you have basically a bond is a line, and then you have two directions. One gives you the causality, where the direction of the effort is, and the half arrow gives you the direction of power. Yes.
Do we have to put the flow on the top of the line and the effort on the side?
Well, that's a-
Can we switch?
Yeah, that's a good question. So Peter Breitman was very pedantic on this, because it's useful notation-wise to say, okay, if I have an half arrow, we could just as well use that asymmetry and put where the half arrow is if I want to notate, for example, the efforts. And I think that was the notation that was using. So if you have an half arrow, so if I write something like this, I'm stopping in that, but it is important actually. So if I write a bond like that, and I want to indicate the two variables like force and velocity, for example, current and voltage, okay, then I would write it then like this. I say, for example, force and velocity, which means this is the effort, this is the flow. Okay. But the issue, you could dualize, you all can always dualize things, we'll see that, and then, you know.
Yeah, but then a follow-up question is that we don't even need to put the flow and effort on the line.
No, well, if you want to do
From
calculations,
point
if you want to do calculation and modeling, it's very useful. We'll see examples of that.
Because from the stroke and the line, I can tell you where the effort is going, from which.
Yeah, but I don't know what it is. So if you want to give variable names, for example, then you need to write it. Like, you know, if you have a block diagram, you want to write what it is, where the lines are, right? It's the same thing. But now you need two things, because every line has two objects related to that conceptual line, right? If you have a block diagram, it's a variable. You just write one name. Now in the bond, you need two, and the question is which is which. Okay, but you have, and of course you can always dualize, because you remember I told you if you have a network, if you have a vector and a dual vector, they are always dual to each other. So you can call this a vector and this is a covector, or you can call this a vector, this is covector in finite dimension. If dimension is a bit trickier, but you can always do that. So you can always dualize things. But it turns out that there is and we actually get rid of this asymmetry, and I will get to that. But it's important to understand at least that it's there. Okay? Yes.
In these notations, if you have the causality, then you immediately think about effort sources. For example, like a battery that sort of specifies voltage.
Yes.
What happens if I have two effort sources, two batteries, dissimilar voltage? How does that work in such a representation?
Yeah, I will get to all this. So you will see when you do the causal analysis, you will find this in one shot. This language is so powerful because all these things is you will never ever have to think anymore. No, in the sense,
promising.
no, in the sense that you will see not only this, because this is what is called the causal inconsistency, but a more clear example is when you have two masses. If you have two masses, then you connect two masses with a rigid rod, okay? And then you model these two masses as two separate masses. But actually, if the rod is really rigid, it's a conceptual thing, because you know there is no rigid rod, because if you hit with the hammer the mass, you will hear the other mass vibrating, because that's, you know, it's not rigid, as we know. But you will recognize that immediately with this language. I will get to all this. It will come all clear. But of course, if you have a source, and I will get to define sources today for sure, you will see that sources are actually the boundary of your physics. Because a battery, for example, a battery, of course, is not a pure voltage, right? A battery has a resistance, and after a while, the battery goes down because the total energy of your system with the batteries is constant, right? So the abstraction you use by saying the battery is a constant voltage, of course, is an abstraction, right? And we'll use this as ideal sources, which usually, if they are constant, are just like a battery. But if we want to do control, we'll have what are called modulated sources, which basically are able to change that value, and you do not give a shit what is coming back because it's always going. It's an ideal, abstraction that is useful in certain contexts, but that really kills the physics for the same reason that the example I gave. Once you say that you can't set something independently of what comes back, that is, you're going out of the physical realm, because that's an abstraction which is not true. It's never true. Okay, I will get to this. But is this clear? This is very important, because as an engineer, we do it all the time. But then you should at least be aware when you do this. Okay, yes?
Maybe you already said it. Basically, effort and flow are two labels that you give to some physical quantity like velocity and force, but you can change them. So once again.
Yes, we'll see all these details. Okay. Yes, the important thing is, now I say voltage and velocity, but the cool thing is that as I try to express when I introduce the first thing, this could be anything. If I give you my robotic bird, okay, and I say part A is the wing, and part B is the air around it, that bond can precisely represent the interaction between the air and the wing. And what you will have is that these two efforts and flow will be fields, of course, because this is a distributed quantity, okay, it's not located, it's a distributed quantity, which can be represented by the motion of the part, for example, the motion of the wing on each point, and the pressure, because you know that, with the air, area, and all these kind of things, because you need forms to do it properly, you just have that. So what you then have, you have a field of velocities of the wing, you have a field of these things, which is pressure times area, which is a form, okay? And then you know that if you pair in each point, that will give you the power density in this point. So if you take the integral around it, you get this. So in infinite dimensional system, nothing changes. It's just that the bond is infinite dimensional. So it is represented by fields that you want to integrate on the boundary. But nothing changes. Conceptually, it's exactly the same. Okay.
But effort and flow, they don't have a proper physical meaning.
No, it's there is a thermodynamical proper definition. I will get to that as well, which tells you what a state is. Once we introduce what physical states are, for example, always learn that kinetic energy is half mv squared, right? Well, it turns out that is properly speaking in this context. You will see why. It's not kinetic energy, it's kinetic co-energy. It's a concept which is very clear. Physics, people in physics do not know this thing. And there is a very big reason why you would call something energy and co-energy. And I will talk about this. And now you can say that if the integral of one of the efforts will give you energy variable, I will talk about all these things. I will get to that, yes.
I know you'll get to it, but so far we've been talking about H as energy.
Yes.
Is this energy?
That is energy.
Okay.
In the classical case, is energy.
Okay.
In the classical physical case, it is energy. Yeah.
We're not. You're not going to tell us in 5 slides that it could also be co-energy. The H, as in, if I take a subsystem,
yes,
it has an energy H, or can it also have a co-energy H?
You can. It's actually information. So if you, it's a tricky thing. So you basically, if you do modeling, you always have a model, and it's kind of it's phantom. It's dual model, and this dual model will then core energy.
Okay.
Okay, and if you connect them together, then you get something very interesting. So and that's something else I'm also writing now. I can tell you the more details here, but it's a bit technical. But it is, if you go to description of waves, that is absolutely fundamental. Okay. So, but in our case, we consider energy. Okay. Other questions? Okay, so this is, the non-causal representation, and the other one is the causal representation. All right, now let's try. There is an issue here because I want to find a way which is completely symmetric. Now I basically said if I write a bond, if I write this distinction with the bond I gave before, I decide what direction of the bond is, and I want a description which is symmetric. So what can I do? Well, I want basically to. If I now put the minus sign here or a minus sign on the flow in this signal in between, what you then would have is that I can consider both sides with the same direction, right? Because I change the power direction. If I put a minus in the effort, so I put a minus in the flow, doesn't matter in which, I change the power direction, right? So if, for example, I have both these sides, this power product of these two things is oriented like that. Okay, the power of these two things now is as a minus oriented like that, right? So by changing the sign of one of the two variables, I invert the direction of the power. Okay. Now,
No, I'm getting lost here.
yeah. Well, you
So-
see it here. You see it in this
So-
picture. So this is what I'm trying to do.
Yeah, but I wonder what you're trying to tell me. Are you trying to tell me that the definition of, for example, effort goes from plus to minus? Because the power flow would be in the same direction, right?
What I'm trying to say is, if I want to describe, this is actually maybe more misleading than helpful, but what I'm trying to say is the following. I want to find a way to describe a system with a certain relations in the same way. So what I want to do, if I want to talk about part one or part two, I would like to have on both sides either the bond toward the element of going out of the element, on both sides. Okay, and in order to do that, I need to change a sign in between. Okay, and it turns out that this is actually deeper than that because it will bring us to Kirchhoff's law. But so far, what I'm just saying, I introduce an element, and you'll see this element is much more powerful, which I call the 1 or a 0, that basically says, in this case, the 0 has efforts on both sides, and the flow switches the sign of the flow. Okay, this is called an effort junction, and this is called the flow junction. Because here instead, the flows are both the same value, but here is swap the efforts, and you see that this element is power continuous. The power that it's consistent with the power because the bond goes both out or both in, doesn't matter. Okay, it's always the power that this is equal to the power of that. If you take the product of this power in that direction, is equal to minus the product of power in that direction all the time. Okay, so so far it seems only a trick and a notation, but you see that it's more powerful than that. And let me get to that immediately, because what I can do, I can say, okay, now all bonds attached at the same flow and for some algebraic. Let me go to this. This is we'll realize. So this is what I did now. Okay. But now what I can do is to generalize this concept. What I can tell you is that, I define an element that says, I call it the 1 junction, and I call it the 0 junction, which will connect different bonds. Okay? And I define these elements in this way. I say, if it is a 1, all the bonds that are attached to that have the same flow. So, each bond has 2 variables, right? That's the point. So I'm saying all the bonds have the same flow. I'm not telling you anything about causality, you see? I'm not putting strokes. I'm just telling you whatever those values are, this element constrains the things which are attached on the other side of the bond such that all the flows are the same. And in order to be power continuous, it means that the efforts will need to satisfy another equation in such a way that the power that gets in is equal to the power that gets out. So you see, there are bonds here that are directed toward the 1, like this one, and there are bonds which are directed outside the 1, Okay? So if I take these products and all these products, that's the power going toward the junctions. If I take these products, the power going out of the junction. And what I'm saying here, I want that the sum of all the power going into the junction should be equal to the sum of the power going out of the junction. It's like, think about this as water, you know. This junction is just redirecting the water on the various bonds, but you cannot store the water somewhere, okay? And to satisfy this, you can do it in this way, or you can do it in that way. So you can say, well, the one junction, you fix all the flows and you algebraically sum the efforts, or you fix all the efforts and you algebraically sum the flows. Okay. And these are Kirchhoff's laws. Okay, the Kirchhoff's laws. So basically, are a way, because now this one junction was, for example, here works with only two objects. But if I have more objects, this basically is a way to say, of these objects that I want to conceptually decompose, I want that they have the same flow, or I want that they have the same efforts. Okay? Is a way to decompose, but then preserving the power flow. Okay? This is Kirchhoff's law, Telegraph theorem, basically. Okay? So this basically is the power continuity, it's related to Telegraph theorem, these are the two Kirchhoff's laws. Okay? So in example, and now I answered the question Peter had. Look, if I want to take sums of these objects, I need to have a sum. That is the vector structure. And you will see it is not, of course, the vector structure is more than that. But you will see that the other operation I do, I will also multiply for a scalar and all this kind of thing. This is precisely what the vector structure gives you. Okay? But you see here that at least I need to be able to sum. So algebraically, I need an operation that sums this stuff. Well, the vector space gives you that operation. It's one of the two operations. All right? An example, and then I can, this is just a trick, okay? Then I can play with this stuff. That would be from the engineering point of view, the useful thing. Because now if you have that, and I want to take the difference between two velocities, but being sure, for example, suppose that these are velocities, because I didn't say, suppose that flows are velocities of mechanical system. And I want to take the difference of two velocities, but then always being consistent in all the efforts that are connected to that. This is what I would do. Look at this. What I have here, if I use the equation, so basically all these bonds, so if I write the one junction now, I know that all the bonds attached to one junction have the same flow. So I can call the one junction as the flow junction, for example. And I can indicate this as the value of the flow at that junction, because everything has the same flow. You see that? So if I have now one junction, okay, and in this one junction there are attached whatever things, and I know that one junction, all the bonds have the same flow, I can just as well say, okay, that the value of the flow is the velocity. Okay, I can give it a representation, okay, because one junction represents the flow that all the bonds attached to it have or need to have. The same way, if I have a zero junction, I can call it an effort junction. I could say, okay, that represents that force. Okay, because I know that all the bonds have the same effort. Now, if I want to do this, and if you write the equation I gave you before, if I now want to say, let's do that, because then I think it becomes clear. So if I use that trick, so I'm saying I have a velocity here. Right? That's the way so a velocity I didn't tell you is a flow. Okay, so it's a flow. I have a flow I call V1. And I had in my modeling another flow which I call V2. And I want to take, because I need that, I want to take the difference between these two flows. Why would you do that? An example, let's take, suppose you have two masses and you have a spring. Okay. The spring is called a nodic element. What does that mean? It means that it doesn't care about the absolute velocities of its sides. The only thing it cares is the relative velocity of its sides. Okay, so if I take the two masses and I move them together, the spring does nothing. Okay, the spring starts to have an effect if I stretch or I compress, right? The relative motions. So the spring is an object which doesn't care about the velocity of this mass or the velocity of this mass. What it cares is the difference of the velocity. Okay? This is called the nodic element. And that's why in electrical engineering, there are only nodic elements. You do not care about the potential of anything. It's always the relative potential of stuff. Yes.
Nodic.
Nodic.
Like node.
Yeah, nodic, yes. So nodicity is a concept in network theory that basically says that if you have an object and you have a relative thing is only related to the relative values of that object, it's called nodic. And in fact, mechanics is a very special domain in physics because position, as we will see, has two roles in nature. Position has a role of configuration and a role of storage of energy. And we will see that this is very special for mechanics. Electrical engineering do not have that. I'm going to be diverging, but nodic means relative in some sense. Okay, so you see that it's relative. If I do an electrical network, of course, let me get to electrical network in a second. So if you have these two velocities and I want to model the mass, so how can I do? Well, I want to have a one junction which represents, for example, V1 minus V2. Or V2 minus V1, it depends, right? So, and how you do it? Well, you know that if you put a zero junction, this is just the thing that if I do this, look, I go from one to the other in the same direction. It can be this, I could do the opposite, doesn't matter. I could do the other way. And then here, for example, I do like this. I could do the opposite. What is important is that these two things are in the same direction, or like that, or like that. Now, let's see what happens. Let's write the equation of this junction. Well, we know that this junction has the same effort, right? So we'll have, the mechanics would be a force. Look at this. That's the force of the spring, by the way, okay? Which has a different sign. We'll get to that, okay? And then here what it says, okay, the sum of the flows that go in, so this thing goes in. And suppose that this is the force, this is the force, this is the force, okay? Same force. Then you know that this is V1, and this is V2, okay? And now the question, what is this guy? Because what is here is this thing, okay? If I write the equation, let's call it delta V now, delta V. And we write the equation, what do we have? We have that this bond goes in, right? So we have V1. Is there another bond that goes in? No, it doesn't. Is equal to, what bonds goes out? These two is equal to V2 plus delta V. Right? So this implies that delta V is equal to V1 minus V2.
I think maybe only didactically, I think what you do under the surface is multiply with the effort.
Sorry?
Right? What you do under the surface is multiply with the effort.
Well,
because the bonds basically tell you that the sum of the power should be the same, right?
Yes, this is this equation, precisely. This is this equation. This equation.
Yeah.
I build this or this such that this is satisfied. Absolutely. Yes.
I understand the central idea.
Yeah.
But if I just look at this diagram, I will have an issue with the one junction on the left or the right. Because this only has power going out now.
No.
It has V1.
No, be careful. It's a convention of positive power. The power can go the opposite direction.
Yeah, but it.
So if V1, look, if V1 times F is negative, the power goes in the opposite direction. It's just a convention of the positive direction of power. The power can go in both directions.
Okay, because I thought the point was that the one junction and the zero junction couldn't add or remove power.
And they don't.
But this one has power going one way, but
no.
There's nothing going into the one from
No. Look. Look. This is just the orientation of the power bond is just what you call positive power.
Yeah.
Okay. So if you write like this and you simulate something.
Yeah.
And you have here 3 and this 5.
Yeah.
The power goes like this. If you have -3 and 5, the power goes in the other direction.
Yes. that's fine.
And it would be such that the power that goes there comes from here or here. Cannot be otherwise. Because this is satisfied all the time.
But the power continuity, in this example, at
Yes.
0, there's power continuity. If I take the h at 0, h dot equals 0.
What is it?
So h is.
There is no power here. There is no storage here. There is
No,
this
but
is just a network.
But at 0, 0 is a part, right? The 0 junction here is a part, like part 1 or part 2.
No. Well, yes, but there is no energy function here.
Yeah,
So
okay,
this is
okay.
a power continuous. It cannot store. It can only distribute energy.
Maybe
Yeah.
I understand
Yeah.
your question. As far as I had my own question as well. So you have the ones on the outside, right?
Yes.
But there's only power going in one direction. So how can it be a one? Why do you start with a one? You understand the 0 in the middle. But
I'm
you don't
doing
understand the
algebra
ones-
now because what I will do in
No,
a
but we don't
moment.
understand the ones on the side. Let's say,
Yeah,
right.
that's my
So
issue.
I'm just doing algebra because then I haven't introduced the element yet.
Mm.
I haven't introduced the masses and the springs. You'll see that what I will then do eventually in bond graphs, the only thing to model this totally, I give you then I will do this. I will just say, okay, here you have a mass. This is a mass. Here you have another mass. This is a mass. Here you have a spring. Done. This is
Okay,
the old
but
bond graph.
this is my issue, right? Is because without those,
Yes.
then the one junctions didn't make sense to me.
No, but now what I'm doing is just
Yeah, you understood the.
No, but what I was saying, this stretch is just algebra. So I'm just giving you the algebraic relation that this network with that junction, because I can do that. I define what a bond is. Every bond has two variables. I give you the equation, so I can give you this algebra. That's what I'm saying. Independently of what I touch to the rest. Because one is an element to which you attach bonds, right? In my notation,
Yes.
I give you a 1 or a 0, and you have I have bonds.
Uh-huh.
And if I attach bonds to it, another junction 1, 0, all over the place, I know that they put constraints on the variables of the bond. That's it. Whatever you attach to this bond is irrelevant. It's a constraint. Okay.
Yeah.
Is it then too far-fetched to say that a 0 can never hook up to another 0 and a 1 can never hook up to
Okay,
another?
you can, no problem. You do it all the time.
But then you have two.
But you need more bonds.
But then you
going
have two
out.
times that the effort is set, right?
So in this case, if you have but this doesn't make
So
sense.
you could shift them into another, I guess.
That's
because-
in fact the operation that you do to simplify. Yes.
Yeah, but so then you could not have a 0. Okay.
These things are, these indeed, what you're saying are simplifications that you do when you do modeling. I will show you. Okay, so for example, just what I want to make now the point is algebraically, very often you take differences of velocity, of potentials. For example, this case is the mechanical thing I said, right? In the case of an electrical circuit, let me give you this. You will not understand the details, but just to tell you what's going on, if I want to model, for example, in a proper way, let's say I have here, a resistor, and I have here a battery, whatever, and then I have an inductor, and here a capacitor, okay? Something like that. So the way you do this modeling, you say, okay, what are in electrical circuits the things that use as reference are the potentials, okay? So this has a certain voltage because it has a potential. So a voltage, it turns out to be an effort. We will see. So I call this a zero junction. This is that potential is the potential of that wire. Here I have another potential of that wire. I represent it with a zero junction. Here I have another zero potential. Represent. Okay. So these are the zero junctions. Represent the potential because our efforts represent the potential of that wire. Now, if I want to attach a resistance now, it is a nodic element. Okay, so so what I do, very simply, just do like this, which is a simplification I already did, because I could have done this, and then this, and then realize that this zero junction is irrelevant if you do the algebra, and I could just attach it there. But these are things I will come to that, but this is what you do. If you want to put the capacitor, you could even do this. Look at this. I could easily do this, but now I choose it like this. And now I put the capacitor, okay? And then the capacitor will be, well, I put a 0 and a 1, doesn't matter in that case, it's 0. But then you will see that I always need, if I have an element of this kind, always the bond toward the element. Now you see now there is a change in sign. You see the bond is not in the same direction. If the bond had been in the same direction, I could have just canceled it. This would not have added any information. But if I have something like this, that's the first example I gave before. If you have a 0 junction or 1 junction in which the bonds are not in the same direction, you have a change in sign. Okay? And then you cannot simplify it like that. Okay? What I could do if I had chosen these bonds like that, I say, well, this is irrelevant. This is just one bond. Just look at the equation, you will see that that's true. And then you would do it for the inductance, that for inductance you would do it like this. And you see, it doesn't matter if I do like that or like that. It always works. So I say like this, and then you have the inductance here. And then here you have one junction, what? And then here are the source of voltage, for example. That's the way you do it. And then you can simplify it. And you will see that, for example, this 0 junction doesn't add anything. You see, it goes through. So I can get rid of this 0 junction. That's just this. Oh, but these are 2 1 junctions, so I can just put everything on the same 1 junction. So, and you do the same here. Oh, this doesn't invert it either, so I can get rid of that. Okay, like that. And well, here I've been choosing it in a different way. There is a change of sign. But now what I can say here, I have this 1 junction. Well, I can simplify it. Just can write. And 1 junction here, and this is what it is. Done. So you see, it's just an algebra of these things. Okay, but then of course, once you get handy, you don't go through everything because you recognize immediately from here that this is just a mesh. So you say all elements have the same current. Okay, but the point is that if you have a complex model in which you have a very complicated network of mechanics of things, in mechanics, references are velocities. In electrical circuits, references are potential, electric potential. And then you take difference of potentials and the other things, you know? Okay, now,
You say velocities are the references in mechanics, is it not the forces?
No.
That will be the efforts, right?
No, but it's I didn't tell you what is what, so that's for a problem. But what it turns out that in normal, and there is a reason for that, that in mechanics, velocities would be flows, and forces would be efforts.
Yes.
Okay, and in mechanics, the reference are always the velocities.
So the flows.
The flows, that's correct. So you put 1 junction all over the place, and then you take difference of velocities.
In electrical networks, you take the efforts.
That's right. So in the electrical network, the potentials are the reference. So you put 0 junctions, and you take the difference of 0 junctions. You give you another 0 junction, which are the nodic value of the dipole or something like that. But we already are doing modeling. I'm not as far, you know. Let's have a break. Now let's see this example. Because now I can do this example, and you see, this is precisely. You could check it that this model, by means of these tricks I gave, is actually this part in which this bond now models this connection. This bond here models the current and the voltage at this point. This bond, try it, check it, okay? And these bonds, it does the same there. So this, you see, you have a bond in and a bond out. It's an open system, which models this part of the network. But now it models it properly. You can attach it as many times as you want. So if you have that model, which now looks very complicated, and of course you could get rid of the 0 junction and do all this simplification. I will do it. But it's just to show here precisely that I just did put the zeros of the potentials here. Okay, and I did the trick I gave on the board. But then if I have this, I touch another time and a third time. And it always is precise. And if you do the simplification, well, it turns out that this is what's going on. Okay, if you do this algebra simplification with the 0 junction and 1 junction, just by using the algebra of the junctions, it turns out that this is the correct model of that. Well, these only has 2 of these things. But this is now correct. And it's still open. I can attach anything here. I can attach a motor. Doesn't have to be the same thing. Anything, this works. in both directions all the time, independent of what I touch here, what I touch there. It's an open model, not like a transfer function. Okay. And of course, it didn't tell you how to model this resistor stuff. That's a different story. But conceptually, you see what I'm doing. Okay. So the junction, it is really the way to model physical interconnection by never losing track of energy flows. Never, ever. It's really the physical modeling thing. It's not a signal mumbo jumbo or artistic drawing of equations via block diagrams. No, it's conceptually keeping the physics.
Well, this is also artistic, eh? Come on.
It's artistic, it's more beautiful, but it also keeps the physics. Okay, but now do you see the difference? So it really, and it's open, it's really open. Now I have a bond here. These bonds, it really gives me this voltage and current here, this voltage and current here. If I now have the model of this network in a library, then I can attach that to anything. That model is the model. And of course, if you want to model this with a different way, well, you need to change it inside. But this is a concept which is called polymorphic modeling, which this group was in the past was very strong. Taylor Fritz did his thesis on this stuff. So basically, you can say, suppose that this would be an electrical, suppose a motor. Huh? What is a motor conceptually? A motor is something you can see an electrical motor as having an electrical port, voltage and current on one side, and a mechanical port, which is the angular velocity and velocity. Okay, and then you can make a model of that. As an object, it has these two ports. And then you can do polymorphic modeling. You can say, okay, I have internally this model or that model, but the ports are the same. So I can use that motor in different situations as an open subsystem. Okay. And sometimes I do the model and you see, well, I think that this is not proper because in this context, I need a more precise internal definition of the motors, for example. The ports stay the same. Okay, so you have a polymorphic, it comes from object oriented. So the type of your model is described by the ports. Okay, and the implementation can have different implementation, but the type is described by the port.
But suppose that you, at some point in time, you recognize that there's too much heat production. You have to add a port, right? So you have to change the model.
If you want to model the heat, look, if you want an electrical model, okay, and indeed it is different, so you need to change the implementation. It doesn't add any ports. If you do not want to describe the thermal, but if you want to, for example, put your motor and you want to look at the cooling that is done on the motor, okay, you need an extra port. There's a thermal port, okay, and the thermal port, we'll see that how it does. You can do that, no problem whatsoever. It's actually the only way. Bond graphs is so powerful in that respect because it really has no limits. You can model entropy generation, heat flows, everything in this always consistent way. Because heat is nothing else than another form of energy flow, heat flow. I will get to that. Okay? But the important thing is open. You see, it's open, and this idea of polymorphic modeling. Yes?
So you need an element to go from one domain to the other?
Excuse me?
You need an element to go from one domain to the other.
Yes, so in thermal, a resistor, that's what we do all the time. We say, a resistor or a damper is dissipate energy. It's wrong. In physics, we know that energy cannot dissipate. It dissipates free energy, which is a Legendre transformation with respect to the temperature. Okay, so that's not correct because when you have a resistor, it's not that dissipate energy. Energy is transferred from electrical to heat. Okay, and because the temperature of the environment is constant, then you can not consider dynamics. We'll see that. But if you want to consider the dynamics and you have different temperature and you want to look at Fourier law for example, heat transduction and this kind of thing, you can do that, no problem whatsoever. Okay.
One question about this circuit. Kirchhoff's laws, beautiful of course, but the voltage law is actually not true for if you have AC currents, right? Because they generate electromagnetic fields, you have induction. So
Kirchhoff's law is always true.
Even if there's induction voltages?
Absolutely. The point is, well, this is not conceptually, I know what I'm talking about. The point is that once you have the model, is not only the Kirchhoff's law, because what you have is that the Kirchhoff's law is in a certain domain. So if you have the network, but you have radiation, energy then is indeed radiated or something like that. It's because your wires, okay, are not just pure wires, are antennas. So you need to model then an object in which that process is described. But the conceptual, these are conceptual Kirchhoff's laws, okay? This is the way I define our conceptual Kirchhoff's laws. Because in the case you have radiation and other things, you will be perfectly able to use this, no problem whatsoever. But these Kirchhoff's laws will still hold as the way I described. But then you will have an object which is not a wire like we use it here, but will be an object in which there will be Kirchhoff's law right and left in this way. But then with this object will have a port which will be wave radiation.
Yeah. And
Okay.
we still have an induction voltage.
Yeah, the point is, you know, the beauty I think is that by using this language, you conceptually really discriminate about these things. You really discriminate about, you know, what are the constraints, conceptual constraints like this, which are, say, the pure Kirchhoff's law. What you're saying is, and there are a lot of these examples, that, you know, some concepts are grouped together and then it's not clear what's going on. Kirchhoff's law is still true in this definition, is the fact that in your modeling, of course, a wire is never a perfect potential everywhere. Because if you go to certain frequencies, okay, the wire does not behave as a, you know, you need to model certain things which are effects which at a certain frequency play a role. So you need to change your model. But a wire, if you see it as a wire, physical wire, as a section on this wire on this side, section on this wire on this side, that's a two-port. On this point and this point. And inside, it could have a radiation, but at that point, there's a voltage and a current, there's a voltage and a current at that section of the wire. If you consider the wire thin enough, because if it's not thin, you have also a circuit of the wire in which you have different currents and different potentials. No problem, you go to fields, you can still do that. So it's all a question of modeling. Conceptually, what I'm saying here works all the time. Once we go to lumped, it's of course an idealization because nothing is lumped. You know, we have fields, we live in fields. So when we say that a wire has a constant potential, is bullshit. Okay? It's true only under certain conditions because we know that there is a field everywhere. Okay? So, and you can do that, but if you want to go to finite dimensional lump modeling, this is what you have. But you can precisely do these things for fields, no problem. I will get to that. I will first I want to do this, and then I will not do that in robotics, but I will talk about in this class if you're interested. I will get to that. Then it fields, Maxwell equations, you know, fluids, you name it. You will see that this works all the time. And of course, for example, also in modeling for complicated, you know, for cardiac, you know, perfusion of bloods in which you have elasticity of the veins, and once we have the computer tools to implement this properly, because also the numerics of this stuff is just magic, you know, these things is bringing answers out of business. I guarantee you. But of course, we need to implement certain stuff. I will get to this. I will defend this statement later. Okay. Now, another example is if you wanted to model this, I gave you the board. See one junction reference of velocity of that mass, reference of velocity of the mass. You know, the springs is actually attached between the two masses, so the velocity difference, if you wish. Okay. And this, of course, is conceptual. You don't understand yet what is going on, but just to show you how you will use the junction at this stage. Okay. Okay. Now we start talking about what we attach with this 0-1 junction. So the atomic elements. Okay. This is really what the issue is. Conceptualize what is storage. The cutting does not always have to be connected by the space. No. Until here's the resistor, until that. Because if you take a resistor, for example, a resistor can have, you know, what we call parasitic capacitance or things like that, right? It is there. It's not that, you know, the capacitance is here and the resistance is there. It's all in one, right? So it's conceptually that you want to model how this is done. So this hearing out does not always have to do with the geometry in some sense, okay? It is a conceptual discrimination. Now, yeah, well, I said this, and these are the zero-one Kirchhoff's law, and then what we want them to describe is, for example, what is storage? How do you model storage of energy? If you have something which has, for example, transfer, changes the relation between effort and flow. We want to try to discriminate about all these elements, and this is what I said, conceptual elements. So storage is one thing, transformation another thing, dissipation is another thing, and then you have ideal sources, which is what Gijs was saying. And unfortunately, I think I didn't. Yes, I wanted to do something. Don't have it here. Damn it. Suppose with your fantasy that I have in my, I always do it with students. Suppose that this is a resistor. I have a real resistor in my hand. It's not a stick. It's a resistor with two wires. Okay. I have a zero. Otherwise, I need to pick it up because I have it in my bag. I have a resistor. How would you define the behavior of this thing?
Well, let's start with Ohm's law.
Does this feel as Ohm's law?
Yes. And a bit more.
Okay, so of course that's the answer I expected. Okay, but it depends in the context. Because if I throw a very heavy resistor in your eyes, you don't care about Ohm's law. Okay, so the point is, what do you want to model? So the model needs to be competent. It needs to describe what you want to model. If you have a resistor and you play basketball with that, you don't care about Ohm's law. Okay, that's clear, right? Okay, so now we'll try to then think about the conceptual thing, because a resistor is an object which has a certain behavior, and we want to model that. So now, what are the storage particulars? Does that store energy? Does that transfer energy to heat? Does that these kind of things? Okay, and the first one we'll do is energy storage. Okay, what is the proper modeling of storage of energy? You need two things. We need a physical state, because when storage is in place in physical modeling, then you're talking about a physical state. And a physical state is a point on a manifold. That's what it is. In physics, all the time, if you think about a physical state, the mathematical structure you need in order to do things is a differential manifold, represent your state space, okay? And a point on that manifold will define the state. Okay? That's the model that you need. And the second thing is you have an energy function. So you have a function that goes from that manifold to a real number. And for given a certain state, that function in that point will give you the energy of that physical state. Okay, this is what the model that we use, and there are reasons to use that. You will see why. And it's important. This physical state is in general not a vector space. It is a manifold. Okay? You cannot sum states. You cannot sum states. Okay, you can see how a state changes and how it evolves. Because that change will give you energy change. Because every point has an energy. Okay. So it does not make any sense to some states. Okay. States are point on a manifold. There is no vector structure here. Yes?
Is it a Riemannian manifold now because define the real number on this manifold?
It's not a Riemannian manifold because it only be the function. And a Riemannian manifold, you would need another structure. We'll see that. So, what the Riemannian manifold is a manifold in which in each point you give a metric, a positive definite metric. It's not the same because I'm giving you in each point I give you a scalar. Tensor-wise, this metric is much more because I give you basically a function is a 0-0 tensor field, right? A function is a 0-0 tensor field. So it's a value in each point. That's what a function is. A metric is a 0-2 tensor field, which is symmetric and positive definite. It's much more structure. Okay, yes?
The energy function can be negative as well.
Sure. Sure, no matter, doesn't
Yeah.
matter, yeah, sure,
Okay.
absolutely. It's just a function, which is smooth, which we need to be smooth for reasons you'll see. And it doesn't even have to be smooth, actually. Well, let's see later. But it's any function which is defined on the manifold. And in classical physics, it needs to be continuous. Classical physics. Okay, is that clear? Now, this is what an energy storage is. And now we want to try to couple this concept to our bonds. How do we do that? Okay, because now we want to say this block now is pure energy storage. We want pure energy storage. So what we want is basically to write the equation in a way that if I take the pairing of these two, okay, because we know that the efforts are covectors with respect to the flow, so it's a pairing, it's power. And if the bond goes toward the element, what we want is the change of this in time should be equal to that. You know, power continuity. The power that comes in is the change of internal energy. Full stop. If that is a pure storage of energy. Okay. That's the atomic element, okay? It's the pure storage of energy alone. Okay? Now, so what we can say is, look, if, you know, inside this storage, the state may change. You know, there is a motion of the points of this state space on the manifold. Okay? And at a certain point in time, you are at a certain point, then you know that you have a certain energy at that time. Okay? If this changes in that point, okay, then there is a change in state. Okay, X dot. And then you know that for what we did, that change in state is a vector in the tangent bound, in the tangent space at that point. Okay, so x of t is a state, x dot of t is the change in state, and is a vector which belongs to the vector space which is tangent to the manifold in x of t. Is that clear? Okay. Now, what we also know, and this is the cool stuff, is that if we have an energy function on the manifold, it turns out, and this is actually something that Frederick did precisely the way he introduced it, it turns out that dV, what is called the differential of V, which is not the gradient, is the differential of V, okay, and I'll show you why it's not the gradient in a second. It turns out to be a covector. So if you have V, dV is actually a 0-1 tensor field. So if I give you a manifold and I give you an energy function, that energy function automatically algebraically defines a 0-1 tensor field. So in each point, you have a dV, okay, which belongs to the dual of space. Okay, and why is that dual? Because of something you have been using all the time, which is the chain rule. If I give you a line, you know, a curve in the state space, what is a curve? Curve in geometry is a function that goes from a real segment to a point in the space in which the curve exists. Okay, so in our case, the segment is time. Okay, you have a timeline, and for each time I tell you what the state is. This time this moves around, and that's a curve, it spans in that time. Okay, and then you have the energy function. The energy function is what? Is a map from the space to the energy of that point, right? Is the function which is there. So this is V, goes from M to R. Okay. So you see that is a composition because now you have a function from T to M, and then you have a function from M to R. M is abstract, you see. It's just a space. It's our manifold. But now you know that you can take the chain rule. If you take now if you take the composition of these two things, so you have a function which is actually from T to R, right? From time to energy, isn't it? So you can take the time derivative of the energy, which is V dot. What is V dot? Well, you know, it's a chain rule. The partial derivative with respect to x times the derivative of x with respect to t. You do it all the time, isn't it? Well, it turns out that is precisely, and in coordinate invariant way, is this guy. is the natural pairing between the velocity at x dot and the differential v, dd. So what you read there, the partial derivative of v with respect to x is actually the differential in the coordinate x that you've chosen. I don't care. You can you choose coordinate x, you choose coordinate y, you choose coordinate z. I don't give it. Okay? You will always get the same thing because it's coordinate invariant. So you see that there is a natural pairing between dd and x dot. And people say, you know, if you have a function like energy, you have a gradient descent and all this bullshit, is not correct. The gradient is not, the gradient is a vector. Okay, in geometry, the gradient is a vector. dd is not a vector, it's a covector. So the only way you can associate a vector to a covector is thanks to a metric. So what I mean is this. And then you see the Einstein notation I introduced. So if I write it with the indices, if I write x dot, I put an index here, right? And if I write dv, I told you this is a covector, I wrote it an index here. Okay, so this is a covector, this is a vector. So when I want to calculate v dot, which is a scalar, that is equal to x dot I dvi. There is a sum you don't see, remember? Okay, it's a sum for I. This is basically this. What I wrote is nothing else than this guy, this operation, okay? Now, people call a gradient is not this guy. This is the differential of v. What people call a gradient is you need to transform this to something that has an index up. How can you do that? If I give you an object which has an index down, which is a covector, how can I go to something which is we call the gradient? So g, no, not g. This is the whatever. Okay. K. How can you go from here to here?
Two-zero tensor.
Very good. A 2-0 tensor. Bingo. So you will need something which is something like this. Right? And then you could do that. This is actually the inverse of a metric. So if you have a metric, if you have a Riemann manifold, for example, in each point you have a metric. That would be the inverse of that metric. And then you can talk about a gradient. But you don't need it. You don't need it. The concept of I introduce here does precisely the same. Okay, but it does not need any metric. It's a purely invariant of the metric. So how do you represent it? Very easy. If I give you now, suppose I have a function which has this minimum here, and these are the what do you call it? The contours of the constant energy. Okay, there's something that comes out of the. It's clear what I'm writing, right? So this is the x, y, and then you have something goes out like that. Okay. Suppose I'm here. Okay. How do you represent? If you remember, if I want to represent a covector, you remember what I told you? What if I give you a covector? What I can uniquely define? I give you a covector. Can I have something represent a covector in the vector space? What is one thing that I can do? You remember the annihilation? If I give you a vector, I can uniquely define a n-1 dimensional subspace in the dual space. If I give you a covector, I can uniquely identify an n-1 dimensional subspace in the vector space. That's what I'm going to do. What is the dimension of the board? 2. So what is 2 minus 1? 1. Can I give you a subspace such that represents the covector? Yes. This guy. If I move along that things, it doesn't change the energy, right? If I move in that velocity, how did I define the annihilator? I define the annihilator as the space of all the duals that pair gives you 0. That's precisely what it is. So you see, the concept of a dual vector is, if you have a contour, are the tangents around the contour. That is the proper representation of the differential dV. So if I give you a function in a certain point, the dV is the plane which is tangent to that in some sense. You don't need any inner product bullshit that you're pushing every book of physics. Okay? So this is really the idea. So dV is a covector, and it represents basically, you know, you can see it as the tangent to the fact that energy is not changing in those directions. Okay?
So if I want to move in the orthogonal direction, I go to any direction.
There is no orthogonal
No,
direction.
I go in a direction which is not in the animator.
Yeah, it's complementary. The only thing, that's very good you say that, because this is the conceptual things you have to be very careful, because you fall into the trap again and again and again. The only thing you can say is either you are in that subspace and you do not change the energy, or you're not. Full stop. It's not that one direction is more than the other. You're not. There is another thing which has to do with optimality and with Pontryagin, because then you can say, okay, what is the direction which maximizes the change? But how can you define it? Because, you know, there is no norm. You know, how can you do that? Those are the things we'll see. But here is no or yes. Yeah? No, we'll stop because it's time. Okay? So let's finish this slide. So you see that what we need is to make this happen. And we want that the power flow is equal to this. But now funny things happen that, you know, people never consider in bone graphs, and also in important Hamiltonian system are not properly well done. Is that the problem that you will see that we'll need a new mathematical object to be precise, because look, I am the gatekeeper. Okay, this flow and efforts can attach on this side to this object and on the other side to something else. These flow and efforts do not know what the state of my system is. Right? Do not know what the state of my system. So I'm a gatekeeper. So if somebody gives me a flow, I need to try to translate that flow to a change in state. But what is a change in state? It has no meaning if I don't know what the state is. Okay. So I need to know what the state is. So I need to say, okay, if you give me that flow, I tell you how much the state changes. So actually, I need to have a map between this and a vector field, because then if I have a vector field, I know where I am, and I can see where I change. You go the algebra in groups. So it turns out that bond structure in geometry needs to be the algebra, but that's something for next time. Okay, questions? You know, all the time when you see these things, people write it like this. All they say, okay, that slope is equal to F, and dV is equal to E. It's conceptually not satisfying, because these things, you know, you cannot look at dV or the velocity independent of the point it is attached. It's conceptually wrong. And this is something that very, very, very few people understand. Okay, so it's pretty deep. We'll get to that, but it's fundamental, because if you want to do multi-body dynamics in robotics, that's why you use Lie algebra. That's the reason. That's the reason. So you have that in all physical modeling systems. If you want to do decomposition, the elements of the efforts and the flow need to be the algebras. You cannot do otherwise, because otherwise you cannot connect states of different systems. But I think you know, even Frederick was, you know, was like surprised about these things. You know, so it's subtle. It's very subtle. Any questions?
Yeah, so this last part, you said that this hold in general, or we have to constrain the state to belong to the X to belong to a limit?
No. It's no. That's what I'm saying is this. the state is a manifold, okay? But if I now, the point is, I need a way to map something outside my model, flow, for example, to a vector fields on my manifold. That's what I need. I cannot do otherwise. Okay, and if I have that map, I know that I have an adjoint map. So it's not a problem. So if I have one map in that direction, the other one is given because of this duality stuff. So how can you define a map like that? You know, what is the structure, once again, the minimum structure you need to express that? And the reason is, if these bonds are attached to these things, on the other side, you will have something else. So you need something that describes the effort and the flow, which is basically, you know, telling how here it's mapped, and there is mapped, and there is mapped. Well, that is the definition of the action of the Lie group. Okay, so it's not the Lie group by itself, but what you want is the action of the Lie group itself. And therefore, it is convenient sometimes to consider that manifold already having a Lie group, because then you know automatically what the action that is.
This is also because the flow and effort, since are elements of one vector space as a dual,
Yeah.
the underlying set may be different from the set which defines the manifold of the
Yeah,
theta such that.
No, it has to do with it. It's not that they are not they are irrelated from each other, because the state is the manifold, which is what it is, and the efforts and the flow are, you know, vector space that describe that things are related. And the only thing you need is to have this map that tells you, if I give you a flow, how does the state changes, as we will see. And of course, you need to have that map for each of the states. Okay, so, well, this by definition is a vector field. Okay, well, this vector field is a map, which is a map from the vector space to a vector field. And what is the way to implement that mathematically is the action on a group. I mean, we'll get to that because some people don't know what that is, but I will talk about this. But that's the mathematical thing that actually solves the problem, because then you have, and that's the reason why I realized when I was in Bologna that, you know, if you write, in my opinion, something like x dot is equal to f of xu as a nonlinear system, is something that it conceptually makes no sense. Conceptually makes no sense, because what is the geometry behind this? What is x is something on a manifold? You know, this is Rn, everything Rn, you can do everything, you know. But the only conceptual thing you can actually write properly in physical terms, I think, is to write something like this, which is what we call, you know, affine systems. Why? Because this is a dynamics, internal dynamics of the vector fields of your system. And this is a reaction of an action of a group or an algebra to the system. It's a map, even it's a map, which is configuration dependent on the manifold that maps the vector input, which should be dependent on the state. Because if it's an input, in physical terms, it should be independent of what the state is, and that's the map you need. Yes?
I have a different question. One thing that stands out to me about the energy functions is that I can, because it's energy function of x, I can have x change without changing v. So I can have x. V is the energy function.
Oh, you mean in case the function as a line is which can change? Yes, depending on the function.
So I can have x dot equals 0.
Yeah.
I'm trying to understand I can have x dot non-zero and v change, but I cannot have v change without x change.
Yes, but then it's a symmetry. Look, you can have a change in state.
Yeah.
But if you have a complete symmetry, that change in state is irrelevant. But you can, of course, if you suppose you have a function like this. You have a function which is here very steep, and then here is very large. And if you move along this minimum, which is the same, you do not observe an energy state change, but you change the state, because then if you are here and you move in different direction, it's different that you were there. So you need to consider that state, right? But of course, if there is a complete symmetry and you move this way and all directions do not change, that's not a state. Because it's irrelevant on that change, it doesn't change anything in your dynamics. So it's, by the model point of view, it's not a relevant change. You see what I'm saying? Other questions?
Stefano, can you hear me? I'm Vincenzo.
Thanks.
Hi, Stefano. I've just a question about, is merely a